recording here. Okay, so we are recording. Okay, we want to solve this initial value problem, this linear system of differential equations. Let me give you a moment to copy it down, okay? Okay, so we have our linear system here of differential equations. You notice the coefficients in front of x1 and x2 are constants, right? There's a 1 there. So this, when you have, well, I want to be a little careful how I say it. When you have other situations, it's more complicated, okay? So, we're not going to integrate here. We don't need to integrate. Good question, Matthew. We don't need to integrate because we know that we can solve this initial value problem by simply finding the eigenvalues and eigenvectors and then creating a linear combination of the eigenfunctions. That's all we need to do. Remember, these differential equations are interconnected. They're not decoupled differential equations because you have an x1 and x2 in both. So let's go ahead and look at the solution. Are there any questions moving forward? And Matthew, it's a very good comment you made, but hold that thought. Hold that thought. Okay, let's move forward. So just to sort of keep us straight on the terminology, you're used to seeing this notation for a linear system of differential equations. X prime of t equals a times x of t. And what I've done was on purpose, I wrote the linear system of differential equations sort of the old, like using the notation you're used to from Calculus 2. But again, this is a linear system, and we can rewrite these two differential equations using matrix notation. And the matrix notation is right here. And of course, that's with the understanding that x prime of t is the vector of derivatives of x1 and x2. The matrix A are the coefficients of x1 and x2. Here's x of t, and here's your initial condition. So now how are we going to find the eigenvalues and eigenvectors? Well, we're going to use this MATLAB command, which you've seen before. And it works fine in this case. And from that, we get the eigenvalues and corresponding eigenvectors. Okay, and you'll have to excuse some of the background noise. I do the best I can. I do the best I can. Okay. Are there any questions up to here? Okay. Yeah, I'm not going to the next page, Matthew. So now that we have our eigenvalues and eigenvectors, wait, question here. I don't know what the third characters are. I know that in MATLAB, if you put this in, you should get this output. What's your question, Matthew? Maybe. Why don't you verbal go like activate your sound and ask your question that way, so I can understand.
What does it say on the left side of the equation?
Where at the bottom?
No, in the MATLAB line that you circle.
Oh, okay. So this is a matrix that holds EVR, eigenvectors, and this is a matrix that holds the eigenvalues. So I just named those. I named them EVR and EVL, but you could use different names. So there's no like, you don't have to call it EVR and EVL. I just use that because it's descriptive. When you use this MATLAB command, it's going to generate eigenvalues and eigenvectors, and the eigenvectors are going to be the columns of this matrix EVR, and the eigenvalues are going to be along the diagonal of this matrix EVL. No problem, Matthew. No problem. You know, questions are good. We like questions. Okay. Well, what would the general solution be to the linear system of differential equations? Well, it's going to be right here, the general solution is going to be a linear combination of the eigenfunctions, and that's what I have right here. And we just showed that a linear combination of the eigenfunctions, okay, remember an eigenfunction is defined as an eigenvector times the exponential function raised to the lambda t power, where lambda is the eigenvalue. Okay, so we just showed that a linear combination of the two eigenfunctions for this matrix A will be a solution to the linear system of differential equations. Okay, given by x prime of t equals a times x of t. Okay, very good, very good, very good. So now, well, all right, this is good, but we need to solve our initial value problem. Remember, this here is a general solution. It's just like in when you took calculus 2, you would find general solutions to differential equations. Okay, like for instance, if you have, again, like a simple example, if you had y prime equals y, okay, I'm thinking math 182 now, then a general solution is y equals some constant times e to the t. Okay, because if you differentiate y prime, you're going to get c times e to the t, and that equals y. So that's a general solution when you have a constant in your solution. But we, in our problem, hence here's my general solution. I have constants too. I have C1 and I have C2. But I'm demanding in the problem that initially at time 0, that x1 is equal to 2.9 and x2 equals 2.6. So, okay, well, I can, solve that. I can solve that, right, by just saying, okay, initially at time 0, x1 is 2.9, x2 is 2.6, and I'm going to set that equal to my general solution where I substitute in time equals 0. See that? Time is equal to 0. So for t, I put in t equals 0. And that's going to give me then a system of linear equations to solve. Please let me know if there are any questions. Oh, IVP means initial, should be initial value. I left out the value. Initial value problem. Thank you, Solman. Please put value here, initial value problem, and I'll fix that on my notes as well. Let me do that. Good catch. This is okay, great. Okay, so now again here we're going to solve this augmented matrix here, and we can use MATLAB to do it because the you know, it's going to be with these decimals here, it can make life a little bit hard, you know. But you want to get out nice fractions because, like, for instance, well, you'll notice that C1 is -3/70 and C2 is 94/35. And in the book for this problem in the textbook, let me see, section 5.7, this problem that we're doing is, let me just make sure, just check the number here. It's for example 2. It's example 2. So in MATLAB, if you want to get nice fractions, you have to use the command format RAT. Okay? Format RAT, and that will give you these, when you solve the system in MATLAB, you'll get those fractions. So there's different commands. You know, there's format RAT, there's format long. If, like, format long is used if you want to have a lot of decimal places. There's different commands in MATLAB that will, you know. All right, so now that we've solved for C1 and C2, well, actually, hold on. Let me go back here. C1 then is -3/70 and C2 is 94/35. But in the book, they write C2 is 188/70. Kind of interesting, but that's what they do. So now we have solved the initial value problem. We've solved it. All right, I'll go to the next page. And here is our solution to our initial value problem. Okay. Solomon, you're good with the previous page? Oh, okay, hold on. All right, let me go back here. Well, you know, see, I'm kind of, I guess I need to ask again. What I've been trying to do, it gets kind of, you know, I'm worried I'm kind of maybe asking too much. Should I move to the next page, you know? So I'm trying to just kind of pace myself as what's reasonable, but I'll ask more because I have to, you know, remember, well, you know, again, you know, if I were in a classroom, I would just look at you all and see if you were caught up. But, you know, all right. So, but I'll tell you what, I'll ask less, but I'll ask more too. All right, if that makes sense. All right. So now, here's our solution to our initial value problem. Very beautiful looking. And the trajectories below. And what I did was I just copied from the book the trajectory, all right? But let me give you a moment to sort of absorb what's on this page. Okay, let me give you a moment to do that. And then we'll talk about this figure. The page that diagram is on in the textbook, it's figure 3. It's on page 316 in your ebook. Okay, so take a moment. No, at least in my, it's 316. I don't know in the okay. I have like the physical textbook. So let me see here. Let me see. In the ebook, yeah, 316. But it's probably like sometimes what happens is the pages in the ebook differ from the pages in the physical textbook. I don't know why, but I've seen it happen, like in WebAssign for some books we use. But I know that this goes with example 2 from section 5.7, this figure 3, and that's probably probably easier just to say that. All right, so let's talk about this figure. All right, so what they're doing here, well, our initial value is 2.9 and hold on here. Yeah, 2.9 and 2.6. So that initial value is the x naught they've drawn in the picture. So that's why it's in the first quadrant. Okay, now what are these trajectories doing? So you know what you're going to do to like follow the trajectory, you have to let time increase, right? You have to let time increase. So looking at the solution here, well, you have two components to this solution. All right. As time increases, what happens to this second component to the solution as time increases? What happens to this part of the solution? What happens to e to the negative t power? What does that go to as t goes to infinity? Good, it approaches 0. It approaches 0. So what's left is when t approaches infinity is just the first part. Just the first part of our solution. Now, you notice in the picture they've drawn a V1 and a V2. Oh, what are V1 and V2 in the picture here? In this figure, they've drawn a V1 and a V2. What are V1 and V2? I also have them, if you notice, I have them highlighted in our solution. Tell me what V1 and V2 are again. Eigenvectors. So they've drawn the eigenvectors. Good, Robin. They've drawn them on the diagram. Okay, so, okay, look at what the solutions are doing here. Okay, so think for a moment what those solutions are doing. I want you to look at it for just a few moments. The solutions are behaving the way they're behaving for a reason. Look at the figure for just a moment. Okay, so first question is the solution, like they draw different particles, okay? They draw different particles. And of course, for our particle, this is the trajectory for our particle. Maybe I'll put it in red. Trying to trace it the best I can. Okay, that's the trajectory for our particle. So, looking at the trajectory, what seems to be just kind of extending a little bit? The trajectory as t gets large, okay, remember, we're letting t increase. This is for, you know, t approaches infinity. Does the trajectory looks like it's parallel to something? If you look at the trajectory, yeah, it looks like it's parallel to what? Parallel to what? I'm thinking of a more like a vector. Ah, that's right, Solman. The trajectory, as t gets large, the trajectory looks like it's parallel to the vector v1. And that makes sense because what happens, and maybe I just want to, let me just draw that trajectory again. And extend it a little bit. It makes sense. Sorry, I want it to look good. I want it to look good. Let me try it again here. Okay. Yeah, I mean, we know based on our solution here that as t gets large, this is going to approach, this component of the solution is going to approach the zero vector for large t, because the e to the negative tth power goes to zero. That means you're going to be left with just this part of the solution for t large. Okay, you're going to be left with just that part of the solution. And you have there, for this part of the solution here, you have a scalar function, negative 3/70 times e to the 16th power times the eigenvector v1. So as t gets large, the solution is a multiple of the first eigenvector v1. And that's what the solution is looking like. That's what this solution here is looking like. And they all look like that. It doesn't matter what the initial condition is. It doesn't matter where the particle starts. All the solutions, as t gets big, follow a path that is a multiple of the first eigenvector. Okay? That's why they say in the write-up here that the direction of greatest repulsion is the line through the eigenvector v1 and the zero vector. Okay? On the other hand, the direction of greatest attraction is the line through the eigenvector v2 and the origin. If you notice, like if this particle here, this particle that we were looking at, going through, starting at x sub 0, if we were to look at time before x sub 0, the particle would be going that way. Well, so I mean, going this way, hold on. Let me just, going this way, this is as t goes to infinity. You know, the particle as time increases. But going this way here, this is as time does what? I'm looking now, I'm looking over here. I'm looking here right now. This part of the particle, which, I mean, the particle started at time equals 0, but if we look before time equals 0, that means time's approaching what? Well, if t's less than 0, I mean, think about the particle. The particle's moving, you know, here's the particle moving. Maybe don't think of time, just think of t. I mean, I think I'm all of this here, all of this, okay, is as t approaches negative infinity. Okay, so this here is as t approaches negative infinity. And as t approaches negative infinity, this part of the solution is going to go to 0. So this part of the solution, I think I can, this goes to 0 as t approaches negative infinity. And this part of the solution, I should say it approaches the 0 vector. This part of the solution approaches the 0 vector as t goes to positive infinity. So in terms of the trajectory, this is why the trajectory is behaving as it's behaving, right? That's why it's behaving as it's behaving. Okay, here at x naught, that's when t equals 0. So I think that's probably the best way to describe it. And this is called a saddle point. saddle point. The origin is a saddle point. So the origin can be a saddle point. The saddle point is when the particle approaches the origin and then repels away as time goes to infinity. An attractor is when the particle approaches the origin and goes into the origin, tracks it. And a repeller is just when the particle never approaches the origin. So you'll have some experience in your homework with this. But are we okay with this diagram? What I wanted to do is I wanted to relate the figure to the solution and try to explain why the trajectory is behaving the way it's behaving. And I think this is the like what I have right here. What I have right here is explains it best. Okay. Are there any questions on that? Kevin's good. All right. Robin's good. All right, great. All right, thank you. I'm very happy. I was a little, I wanted to make sure you were comfortable with this. So look, hey, we had some real eigenvalues in this problem and we got real eigenvectors. But hey, what if we had complex eigenvalues? I mean, we know that can happen. That can happen in differential equations. You can get complex eigenvalues and eigenvectors. So we need to look at a problem that deals with that. We need to look at a problem that deals with that situation. And so for that, I have yet another example. So give me a moment to upload it. I'll be right there. Okay, so everybody's good? We'll move on. All right, let me bring up the next file here. Perfect. Okay, so okay, let me stop the recording.